coffee-powered cars to planes running on used cooking oil, engineers have found some surprising ways to keep vehicles moving without traditional fuel. In today's video, we're going to take a look at 15 vehicles that run on weird fuels. Starting with number 15, the Saab 9.5 Biopower. In the mid-2000s, when most automakers were just chasing efficiency through hybrids and early electric prototypes, Saab took a different route. The Swedish manufacturer introduced the Saab 9.5 Biopower, a sedan that could run entirely on E85, which is a blend of 85% ethanol and 15% gasoline. Now, while ethanol had long been used as a fuel additive, Saab's approach was different. It designed an engine that not only tolerated the biofuel, but actually performed better on it. The 9.5 Biopower was launched in 2005 and was powered by a 2-liter turbocharged engine modified for ethanol use. The company used the fuel's higher octane rating to increase the turbo boost pressure. That resulted in more power, 180 horses on gas and up to 210 horses on E85. The result was one of the few production cars that became faster when filled with biofuel. Technically, the car wasn't alternative in its design. It still used an internal combustion engine, but it showed how small engineering adjustments could make renewable fuels viable without any major redesign. Drivers could switch between gasoline and ethanol seamlessly, even mid-tank, which made it practical in regions where E85 wasn't always available. The ethanol for the 9.5 Biopower was primarily sourced from biomass, like sugarcane, wheat, or corn, depending on the regional availability. In Sweden, much of it came from domestically produced biomass, which did reduce the car's life cycle carbon emissions compared to gasoline. At the time, it claimed up to a 70% reduction in CO2 emissions when ethanol was produced sustainably. However, it faced limitations outside Sweden. Infrastructure for E85 fueling was sparse in most of Europe and North America, and consumers were, hesitant to trust biofuels as a long-term solution. And still though, the car received positive attention for its clever engineering. When Saab eventually went bankrupt in 2011, the Biopower program ended quietly, but its legacy remained. It paved the way for further research into next-gen biofuels like cellulosic ethanol and synthetic alcohol fuels. In an era before electric vehicles took over the sustainability spotlight, the 9.5 stood out as a practical demonstration of what could be achieved when engineers reimagined traditional engines. Number 14, the BMW Hydrogen 7. In 2006, BMW unveiled a bold production car, the BMW Hydrogen 7. It looked like a standard 7 Series luxury sedan, but beneath the hood was an engineering experiment that bordered on the improbable. A 12-cylinder engine capable of running on both gasoline and liquid hydrogen. It wasn't a concept car, but a limited production model. A small fleet of them was actually leased to a high-profile individual and institution for real-world testing. The engine was based on BMW's 6-liter V12, which was modified with a dual-fuel system. Drivers could switch between the gasoline and hydrogen at the push of a button, and with the engine automatically adjusting the fuel injection and ignition timing. When running on hydrogen, it produced almost zero CO2 emissions, just water vapor was the main byproduct. Their goal was to prove that internal combustion engines could coexist with hydrogen tech, offering clean power without abandoning the performance and sound that defined the brand. However, using liquid hydrogen as a fuel did present some major challenges. Hydrogen becomes liquid only at -253 degrees Celsius, and that requires heavily insulated cryogenic storage tanks. The Hydrogen 7's fuel tank, built from aluminum and carbon fiber, could hold about 8 kilograms of liquid hydrogen. Even so, though, it slowly boiled off over time, meaning the car would lose fuel if left unused for too long. Its range was about 200 kilometers, after which the driver could switch to gasoline for another 500, and BMW collaborated with Shell to create a small network of hydrogen fueling stations in Germany, but the infrastructure remained limited. The performance was pretty good. The car could accelerate from 0 to 100 kph in about 9.5 seconds and reach a top speed of about 143. BMW also emphasized the refinement of the combustion process. They ensured smooth operation and low noise levels compared to its gasoline counterpart. In hindsight, the Hydrogen 7 was more of a technological milestone than a real practical product. The complexity, the cost, the fuel storage limitations, it all made mass adoption impossible. Yet it remains one of the most remarkable attempts to run a high-performance luxury car on one of the universe's simplest elements. Number 13. The Volvo LNG Truck. Now, while passenger cars often get most of the attention when you discuss an alternative fuels, some of the most meaningful innovation has taken place in heavy transport. The Volvo FH LNG truck is a prime example. It's a long-haul commercial vehicle that runs on liquefied natural gas, or LNG, a fuel made by cooling down natural gas until it becomes a liquid. LNG takes up way less space than its gaseous form, and it makes it practical for heavy-duty trucks that need large energy reserves. Volvo introduced it in 2017 as part of its effort to reduce CO2 emissions from freight transport without sacrificing performance. It's powered by a modified 13-liter Volvo engine that uses compression ignition, which is similar to a diesel engine. This design allows it to deliver almost identical torque and power to its diesel counterpart, and it emits 20% less CO2. The fuel system is engineered to keep the LNG at cryogenic temperatures in insulated tanks, where it stays in liquid form until injected into the engine. Once in the combustion chamber, the LNG is mixed with a small amount of diesel fuel, used as an ignition source, to start the combustion. This hybrid approach maintains its reliability while still delivering substantial emissions reductions. The truck was aimed at long-distance freight operations with ranges that exceed 1,000 kilometers per tank, and Volvo also worked with fuel providers across Europe to help expand the LNG refueling infrastructure. While LNG is still derived primarily from natural gas, the lower carbon output make it realistic as a transition fuel until electrification becomes more viable for long-haul transport. Volvo managed to make an unusual fuel, stored at cryogenic temperatures, work seamlessly in a sector that's not known for embracing change. It's not a concept or an experiment. It's a working solution already moving goods across Europe, proving that the road to cleaner transport can sometimes be paved with LNG. Number 12. The Tesla Semi Megacharger Network. Although the Tesla Semi itself is an all-electric truck, what makes it relevant to unusual fuels is not the vehicle alone, but the infrastructure designed to power it. Tesla announced in 2017 that its Semi would eventually be supported by a network of megachargers, high-capacity charging stations powered directly or indirectly by solar energy. In this case, sunlight itself becomes the fuel, stored and delivered through electricity rather than burned. The powertrain relies entirely on electricity with 4 independent electric motors capable of delivering over 1,000 horsepower combined. Now, unlike LNG, biodiesel, or hydrogen, it's got no combustion component at all. Now, what's unusual in Tesla's plan to pair the trucks with dedicated solar installations, ensuring that the electricity used for charging is renewable and free of fossil input. Each megacharger is designed to deliver over a megawatt of power, roughly 10 times the rate of the Tesla standard supercharger for passenger cars. This allows the Semi to recharge up to 70% of its battery capacity in about 30 minutes. Now, solar energy as a fuel may not be new in theory, but Tesla's approach was unusual in execution. By combining large-scale solar arrays with stationary battery storage at the charging sites, the company can deliver reliable, high-speed charging even when the sun isn't shining. In locations like Nevada and California, Tesla's already installed solar-powered charging sites that support both passenger vehicles and early versions of the Semi. Its battery system converts roughly 95% of the stored energy into motion, compared to just 35 to 40% for a typical diesel engine. And Tesla claims the truck can achieve a per-mile energy cost roughly half that of diesel trucks. Early prototypes showed ranges of up to 800 kilometers, that's 500 miles on a single charge, though the final production figures will depend on configuration and payload. While skeptics note that building a truly global solar-based megacharger network is logistically unfeasible, the project does mark one of the first large-scale efforts to treat renewable energy as a fuel infrastructure, not just a power source. In many ways, the Tesla Semi shows the far edge of the unusual fuel spectrum. If fuel isn't mined, refined, or piped, it's harvested from space, converted into electrons, and delivered silently through copper cables. It's as close to modern transportation gets to running on pure sunlight, a concept that was once the stuff of science fiction, but now it just rolls quietly down the highway in prototype form. Number 11. The Toyota Mirai. When Toyota unveiled the Mirai in 2014, it wasn't just releasing a new car, it was presenting a blueprint for what a post-petroleum world might look like. The name Mirai means future in Japanese, and that was exactly the company's ambition, to make hydrogen fuel cell vehicles not an experiment, but a practical road-ready technology for everyday use. Now, at first glance, it looks like a sleek mid-size sedan, but under the futuristic exterior is a system that's fundamentally different from any gasoline or diesel car. Its propulsion relies on a fuel cell stack, which is a device that generates electricity through an electrochemical reaction between hydrogen and oxygen. When the hydrogen gas from the car's tanks meets the oxygen from the air, the atoms are combined inside the fuel cell, releasing electrons that flow through an external circuit, creating the electric current to power the motors. This technology isn't new, in theory. Fuel cells have existed since the 19th century, but Toyota was the first automaker to mass-produce it for the consumer market. The powertrain of the Mirai has two main hydrogen tanks made of carbon fiber reinforced plastic that holds gas pressures at about 700 bar, that's 10,000 psi, and together they store roughly 5 kilograms of hydrogen, which is enough to drive around 650 kilometers or 400 miles. The hydrogen's fed into the main fuel cell stack, which then generates about 128 kilowatts, roughly 172 horsepower. It can convert about 60% of the hydrogen chemical energy into usable electrical power, which is roughly twice as efficient as an internal combustion engine. And for drivers in areas where hydrogen stations exist, the experience of owning one is pretty normal, quiet, smooth, and odorless, yet entirely free of fossil fuel emissions. The biggest challenge, though, lies not in the car itself, but the fuel supply. Hydrogen has to be produced, stored, and distributed safely and economically, which requires substantial infrastructure. In Japan, California, parts of Europe, hydrogen refueling networks have slowly expanded, but globally they remain rare. Critics of hydrogen vehicles often point to inefficiencies in production. Most hydrogen today is made from natural gas through a process called steam methane reforming, which releases carbon dioxide. However, when the hydrogen is produced through electrolysis using renewable energy, the entire chain becomes effectively carbon-free. By 2020, Toyota released a second-generation Mirai, addressing some of the first model's limitations. The new version improved the range to over 650 kilometers, increased the power output, and featured a more conventional design. Toyota also lowered production costs, hoping to make hydrogen cars accessible to a broader audience. Each vehicle sold shows a complete closed-loop system for clean mobility, from fuel generation to motion to emission-free exhaust. It's also influenced other automakers, including Hyundai with its Nexo and Honda with its Clarity fuel cell, pushing hydrogen fuel cells from the realm of concept into the reality of public roads. Number 10. The Peel P50 Coffee Car Conversion. So among the strangest and most memorable experiments in alternative fuels, few are as charming or as improbable as the so-called coffee car, a tiny Peel P50 converted to run on coffee grounds. Originally designed in the early 1960s as the smallest production car ever made, the Peel P50 was a three-wheeled microcar just over 4 feet long and barely weighing 130 pounds. It was never meant for innovation in fuel systems, but decades later, British engineers used it to make a statement. If something as ordinary as coffee waste could power a car, then almost anything organic could. The concept started in 2010, led by a team of engineers and advocates working with UK-based research project called the Coffee Car. Their goal was to demonstrate the potential of biomass gasification, which is converting organic waste into a combustible gas. The project followed earlier experiments that used coffee grounds to power a Volkswagen Scirocco and a Ford pickup truck, but using the tiny Peel P50 added a mix of humor and ingenuity that drew public attention. The fuel process worked like this. Used coffee grounds were dried and placed into a gasifier mounted to the vehicle. When heated in a low-oxygen environment, the coffee broke down chemically, releasing a mix of hydrogen, carbon monoxide, and methane, collectively known as syngas. This syngas could then be piped into an adapted internal combustion engine where it burned, much like natural gas or propane. From a scientific standpoint, the experiment relied on the principles already used in large-scale energy production, and during World War II, hundreds of thousands of vehicles in Europe were equipped with wood gas generators that worked on the same principle, allowing them to operate during petroleum shortages. The coffee car simply applied that wartime ingenuity to a 21st century context, with a modern twist and a familiar aroma. It turns out that coffee waste contains about 10 to 15% oil by weight, which can be chemically processed into fatty acid methyl esters, the same compounds found in conventional biodiesel. But in the case of the Peel P50 project, however, the value wasn't in efficiency, it was in symbolism. The car became a demonstration of sustainable energy possibilities. Even materials as mundane as coffee waste can, with some ingenuity, be turned into motion. The coffee car project attracted enough attention to appear on TV, including BBC's Bang Goes the Theory, where it successfully ran on roasted coffee pellets. Although impractical for daily driving, the experiment did raise awareness about bioenergy. Today, the original converted Peel P50 survives as a novelty exhibit in the UK and occasionally revived for demonstrations. The message it had was simple but profound. Fuel is not defined by what it's made from, but by the creativity of those willing to imagine new uses for the resources we throw away. In that sense, the world's smallest car made one of the world's biggest statements, powered not by gas, but by the morning leftovers. Number 9. The Airbus A380, flying on used cooking oil. In November of 2021, Airbus conducted a really cool demonstration, a full test flight of its A380 Super Jumbo, powered entirely by sustainable aviation fuel, or SAF, derived from used cooking oil and animal fats. The event was a clear signal that the world's largest passenger aircraft could, in theory, operate without a drop of fossil-based jet fuel. This wasn't a futuristic concept or lab experiment either. An actual A380 took off from France and flew for 3 hours on fuel made from recycled waste oil. Sustainable aviation fuel is chemically similar to standard jet kerosene, which is known as Jet A1, but it's produced from renewable sources like used cooking oil, agricultural residue, or even municipal waste. For the test, the Airbus filled one of the A380's Rolls-Royce Trent 900 engines entirely with this fuel. The flight showed that the engine performed identically to when running on conventional jet fuel, with no adverse effects on performance or emissions. The key difference was in the carbon footprint, because the fuel was made from waste oil rather than crude petroleum. This A380 flight was part of a broader effort by Airbus, Rolls-Royce, and several European energy firms to prove that SAF could power modern commercial craft. The test was followed by similar flights on smaller models like the A320neo and A350, and Airbus has since committed to certifying all of its aircraft to operate with 100% SAF by 2030. This flight also addressed one of the biggest questions: performance. Engineers monitored the engine efficiency, the fuel burn, and exhaust emissions, and found no measurable loss in thrust or reliability. Since that 21 flight, other major airlines have followed suit. British Airways, KLM, United Airlines, and Singapore Airlines have all begun using SAF blends on commercial routes. Now, while global supply remains limited, less than 0.1% of aviation fuel used today is sustainable, the technology has proven itself beyond a doubt. This test flight on used cooking oil wasn't just a publicity stunt, it was a demonstration that even the most demanding machines can adapt to cleaner energy. It showed that waste, when processed correctly, could lift a 575-ton aircraft into the sky. Number 8. The Audi A4 Avant G-Tron. So Audi A4 Avant G-Tron is one of the few production cars designed to run on both compressed natural gas and a synthetic alternative fuel known as e-gas. It is an unusual pairing, one fuel drawn from underground natural gas deposits, the other produced in a lab from thin air and renewable power. Launched in 2017, the A4 Avant G-Tron was part of Audi's broader initiative to explore synthetic fuels. Its 2-liter turbocharged engine was modified to handle methane instead of gas, and under the cargo floor, Audi fitted 4 lightweight tanks made of carbon fiber and polymer that stored compressed gas at 200 bar, that's about 2,900 psi. Together, they hold enough energy for about 310 miles of driving. When the tanks run empty, the engine automatically switches to gas, which extends the total range to more than 900 kilometers. The process of generating e-gas begins with surplus electricity from wind turbines or solar farms. This renewable power drives an electrolyzer that splits the water into hydrogen and oxygen. The hydrogen is then combined with carbon dioxide, captured from industrial sources or biogas plants, and creates the methane through a reaction known as methanation. The result is chemically identical to natural gas, but its production removes CO2 from the atmosphere instead of adding more. From a performance standpoint, it behaves almost identically to its gasoline counterpart. It produces 170 horsepower and about 270 newton-meters of torque. It accelerates smoothly and emits up to 80% less CO2. Maintenance intervals, too, are unchanged, as the engine runs cleanly enough to produce significantly lower particulate and NOx emissions than diesel engines. By using renewable electricity to create fuel rather than charge batteries, it provides a way to store energy long-term and use it in existing engines and infrastructure. In this sense, the G-Tron is less about replacing the combustion engine and more about reinventing what goes into it. But producing e-gas remains expensive, and the amount generated by Audi's facility is very tiny compared to total fuel demand. Still though, the system proved that the concept works. Electricity can be converted into fuel, stored in pipelines, and burned cleanly in conventional engines. But Audi has since discontinued the G-Tron line to focus on electrical vehicles. Moving on to number 7, the Boeing Phantom Eye. When Boeing unveiled the Phantom Eye in 2010, it didn't look like a typical aircraft. Its long wings stretched nearly 150 feet, and it had the serene, bulbous shape of a glider rather than a jet. This was no ordinary plane. It was the world's first high-altitude, long-endurance, unmanned aircraft, powered entirely by liquid hydrogen. Its mission was to stay aloft for days at a time without refueling, quietly cruising at 65,000 feet in the stratosphere. Liquid hydrogen was chosen because it contains about 3 times more energy per kilogram than traditional jet fuel. However, using it requires some clever engineering. Hydrogen has to be kept at very cold temperatures, negative 253 degrees Celsius, to remain in liquid form, meaning the Phantom's Eye's tanks needed to be cryogenically insulated. Boeing developed custom carbon composite fuel tanks that could withstand the enormous pressure difference. The propulsion system was built around a 2.3-liter 4-cylinder engine derived from Ford trucks, but heavily modified to run on gaseous hydrogen. Each engine produced about 150 horses, which was sufficient to keep the aircraft aloft for up to 4 days without landing. The fuselage was wide but light, the large central cavity to house the insulated tanks, and the wings were extraordinarily long to maximize lift. Unlike jet engines, the Phantom Eye's propellers turned slowly and quietly, giving it an almost silent presence. Boeing envisioned it as a future platform for environmental monitoring, communications, and maybe surveillance, roles where long endurance and zero emissions were paramount. It had its maiden flight in June of 2012 at Edwards Air Force Base in California. It lasted just 28 minutes and reached an altitude of 4,000 feet before landing safely. Although a minor landing gear issue did damage the aircraft slightly, the test proved that liquid hydrogen propulsion could work reliably in a high-altitude drone. Over the next few years, Boeing refined the system and achieved higher and longer flights. But what made the Phantom Eye really important was its use of combustion hydrogen rather than the hydrogen fuel cells. The result was a simpler, lighter system capable of producing power for flight while maintaining zero carbon emissions. Number 6. The Biobus. So in 2014, residents of Bristol, England began seeing an unusual bus making its rounds between Bath and Bristol Airport. It's painted with light-hearted graphics that showed smiling bubbles and labeled the Biobus. It quickly earned a more memorable nickname, the Poo Bus. The name was literal. This public transport vehicle ran on biomethane gas produced entirely from human waste. Its goal was to demonstrate how everyday waste could be turned into clean, renewable energy. The bus itself was a modified Scania Enviro 300 fitted with a 1,000-liter gas tank on the roof that stored compressed biomethane at high pressure. But the real innovation lay beneath the streets. The fuel came from Bristol's sewage treatment works, where Geneco operated an anaerobic digestion facility. They used microorganisms to break down the sewage and food waste in oxygen-free tanks, releasing a mixture of methane and carbon dioxide, or biogas. The methane was purified to remove the CO2 and impurities, leaving biomethane suitable for vehicle fuel. Each tank of gas could power the bus for around 186 miles. It was an attention-grabbing way to convey a serious point. Waste, properly managed, could be a renewable resource. The biobus emitted almost no particulate matter and drastically reduced any NOx emissions compared to diesel buses. Its performance was comparable to that of a conventional vehicle. It could carry up to 40 passengers, accelerate smoothly, and reach normal road speeds. Refueling took place at a biomethane station built specifically for the project. Maintenance requirements were minimal, and the engine ran more quietly than a diesel equivalent. But the public reaction to the bus was a mix of amusement and admiration. The media quickly dubbed it the bus powered by poo. But the humor helped attract global attention to this serious environmental innovation behind it. It became the world's first commercial bus service fueled entirely by human and food waste. Number 5. The ZEP Hybrid Airship. Developed by Lockheed Martin, the ZEP hybrid airship, and operated in various forms under different names, represented a fascinating blend of old and new technology. Combining buoyant helium lift with conventional jet fuel propulsion, this hybrid airship is designed to carry heavy cargo to remote areas while using less fuel than airplanes or helicopters. This unusual fuel isn't just one type, it's a hybrid relationship between two forces, the lifting power of lighter-than-air gases and the thrust of combustion engines. Unlike classic airships like the Hindenburg, which relied entirely on buoyant gas, the ZEP hybrid uses about 80% static lift from helium and 20% dynamic lift generated by shaping and propulsion. Power comes from 4 turboprop engines that burn standard jet fuel, but because the helium provides so much lift, the fuel consumption is drastically lower than a traditional craft. For instance, the airship can carry up to 20 metric tons of cargo using about 1/10 the fuel of a comparable plane. Its structure is built from advanced composite materials and high-strength fabric envelopes that contain the helium, and unlike old Zeppelins which used a rigid airframe, the ZEP hybrid airship uses a semi-rigid hull that's supported by slight internal pressure. The design was originally developed in the 1990s for U.S. military's Aeroscraft and P-791 prototypes, and later refined for commercial logistics. It could deliver large, heavy payloads without building any roads or runways, which made it ideal for remote infrastructure projects. In trials, the airship proved remarkably stable. It could hover in place like a helicopter, cruise at about 120 knots, and fly at altitudes of up to 10,000 feet. The propulsion system, though based on standard kerosene, effectively became an unusual fuel system when paired with helium. By combining a fossil fuel engine with a buoyant gas, the ZEP hybrid airship turns an element of the universe into a silent partner in propulsion. If deployed at scale, it could transform how freight moves across difficult terrain, merging 20th century engineering with 21st century sustainability goals. Number 4. The Chevy Silverado E85 NASCAR truck. So in motorsport, speed and sustainability rarely intersect. For decades, racing engines have been synonymous with high-octane gasoline and roaring emissions. But in 2011, NASCAR began one of the most successful real-world experiments in alternative fuels, when it switched its entire racing series, including the trucks like the Chevy Silverado used in the NASCAR Camping World Truck Series, to E15 and later E85 ethanol. The E85 variant, which is a blend of 85% ethanol and 15% gasoline, is one of the most unusual fuels ever used in a professional motorsport. Ethanol used in NASCAR is not the same as the alcohol in beverages, though. It's industrial-grade biofuel that's produced from fermented cornstarch or other biomass, then distilled and blended with gasoline. The racing fuel is supplied by Sunoco under the name Green E15 and is formulated to meet strict performance standards. Once optimized, the engines showed no less speed or durability. In fact, many teams reported slightly cooler engine temperatures and cleaner exhaust. On the practical side, it reduced greenhouse gas emissions by about 20% across the sport's fuel consumption, cutting thousands of tons of CO2 annually. And symbolically, it showed to millions of fans that renewables were not limited to eco-friendly city cars. They could power high-performance machines at 200 miles an hour. It was subtle, but a powerful counter to the idea that green energy must mean slow. For Chevrolet, the experiment also served as a real-world R&D for its fuel production vehicles, which could run on E85. Lessons learned on the track, especially in fuel injection and sensor calibration, filtered down into the road cars like the Impala and the Tahoe Flex Fuel models. Today, NASCAR's ethanol program is considered a success story. What began as an experiment is now a standard across all 3 national series. Each race weekend, it shows loudly that renewable fuels can compete head-to-head with petroleum. The Silverado E85 racing truck, roaring down the track, that became a symbol of that unlikely marriage of sustainability and speed. In the high-octane world of motorsports, that's as unusual and as meaningful a fuel shift as any in modern transportation. Number 3. The Alstom Coradia Island. In 2018, a quiet revolution took place on Germany's regional railways. A sleek blue train rolled out of a station in Lower Saxony, humming softly instead of roaring. It was the Alstom Coradia Island, the world's first commercial passenger train powered entirely by hydrogen fuel. Hydrogen-powered trains like this one were designed to solve a very specific problem. Thousands of regional train routes in Europe are not electrified. Installing overhead power lines across those lines is expensive and disruptive, yet diesel locomotives that serve them are noisy, dirty, and emit large amounts of CO2. The island offered a third option: quiet, zero-emissions operating using an onboard hydrogen power plant. The train's roof has large hydrogen tanks, each holding gas compressed at about 5,000 psi. The hydrogen is fed into a fuel cell stack where it reacts with oxygen from the air to produce electricity. This powers two traction motors with a combined output of about 800 horsepower, and the only byproduct is pure water vapor, which exits through small vents along the roof. The island also has these lithium-ion batteries that store excess electricity for acceleration and capture energy through regenerative braking that's similar to hybrid cars. When coasting or braking, the batteries recharge. When extra power is needed, they assist in the fuel cells. On a full hydrogen tank, the island can travel up to about 620 miles and reach speeds of about 87 miles an hour, which matches the performance of diesel trains on similar routes. For the German network, Alstom partnered with the energy company Linde to build the first hydrogen train refueling depot, which uses renewable energy to produce hydrogen through electrolysis. Following the success of the initial deployment in Germany, Alstom expanded hydrogen train service to other European countries including France, Italy, and Austria. The companies partnered with Canadian and UK rail operators for future networks, and by 2022 they had logged over 100,000 kilometers of commercial operation. And of course, the island's success has spurred competitors like Siemens and Stadler to develop their own hydrogen-powered models, and together, these trains may soon transform Europe's non-electrified railways, eliminating diesel emissions across thousands of kilometers of track. This train shows that progress doesn't always come with noise, and the cleanest journeys can run on the simplest element in the universe. Number 2. The Eco Marathon Urban Concept Car. Every year, teams of engineering students from around the world compete in the Shell Eco Marathon, a competition that challenges them to design vehicles capable of traveling the greatest distance on the least amount of fuel. These vehicles are not theoretical. They're built, tested, and driven on real circuits, and the goal isn't speed, but efficiency, and the results do push the limits of what's possible in fuel economy. One of the most unusual categories in the competition is the Urban Concept class, which requires vehicles to resemble small, practical city cars rather than futuristic streamliners. Over the years, teams have produced working vehicles that can travel over 1,000 kilometers on a single liter of fuel, or its equivalent, powered by energy sources far removed from conventional gasoline. In 2010, for instance, a team from Laval University in Quebec developed a hydrogen fuel cell car that set records for efficiency, traveling nearly 5,000 kilometers per kilogram of hydrogen. It's equivalent to more than 12,000 miles a gallon of gasoline. The fuel cell was compact, lightweight, and paired with a brushless electric motor, and the entire vehicle weighed less than 220 pounds, and it could reach speeds of about 25 miles an hour. Another standout came from Indonesia's university, which built a small car running on used cooking oil converted into biodiesel. The team collected oil from campus cafeterias, filtered it, and processed it into methyl esters using a transesterification reaction, essentially the same process used in commercial production. Their car completed race circuits powered entirely by this recycled fuel, showing how waste streams can become viable energy sources. But what makes these vehicles interesting is their direct educational impact. Each is designed, built, and driven by students under strict efficiency and safety rules, and teams learn firsthand about energy conversion, emissions, and life cycle impact. Though the vehicles are not intended for commercial use, many innovations born from this challenge influence real-world designs. Advances in lightweight materials, hybrid drivetrains, and aerodynamic efficiency have filtered into consumer vehicles. And the Eco Marathon trial continues to evolve, now including electric, hydrogen, and biofuel categories across events in Asia, Europe, and the Americas. It's kind of like a living laboratory for alternative energy. It's a place where students test not just the new fuels, but new ways of thinking about transportation. Whether powered by hydrogen, ethanol, or waste oil, these student-built cars show us that innovation often starts small, in a garage, a lab, or even a classroom, and that the next revolution in mobility might just begin with a few liters of something no one thought could move a car at all. Number 1. The Aptera Solar Electric Vehicle. When the Aptera solar electric vehicle emerged from a California startup in 2020, it looked more like a small aircraft than a car. With 3 wheels, a teardrop body, and built-in solar panels across its roof, hood, and dashboard, the Aptera wasn't designed around gasoline or even hydrogen. Its primary fuel was sunlight. Unlike conventional electric cars that need to plug into the grid, this one could charge itself directly from solar energy, turning the car itself into a moving power plant. The company claimed the vehicle could travel 40 miles per day purely on solar charging, depending on location and weather. The built-in solar array made from high-efficiency cells integrated into the car's curved surface could generate up to 700 watts of power under optimal conditions. For longer trips, though, the car would likely still be charged as a standard electric vehicle, but for day-to-day use it relied entirely on natural light. Its lightweight carbon composite body weighed less than 2,200 pounds, and the aerodynamic drag coefficient is just 0.13, which is way lower than any production car. The three-wheel configuration and narrow front area allowed the vehicle to travel over 1,000 miles on a single full battery charge, while supplemented by a solar input. Unlike other solar cars that existed only as prototypes or competition vehicles, this one's goal was to bring the technology to consumers. And while the idea sounds futuristic, it is based on solid science. Solar radiation delivers about 1 kilowatt of energy per square meter under full sun. Covering a car's exterior with these high-efficiency cells can realistically generate a few kilowatt hours of electricity per day. Aptera simply pushed the concept to its logical extreme by designing the entire vehicle around minimizing energy consumption. The Aptera's creators, Chris Anthony and Steve Fambro, first attempted to bring the idea to market in 2008, but the financial crisis and lack of investors led to the company's collapse. But more than a decade later, advances in lightweight materials, battery chemistry, and solar efficiency made the project feasible again. In its current form, it's built around modular components, a composite monocoque chassis, embedded photovoltaic cells, and battery packs that range from 25 to 100 kilowatt hours, depending on range preference. But the car's efficiency is so extreme that its electricity consumption is measured at less than 100 watt-hours per kilometer. That's roughly 1/3 of that of a Tesla Model 3. When charged purely by sunlight, its operational emissions drop to zero. There are, of course, limitations. The small size and unconventional design restricts seating to 2 adults and limited cargo. Solar charging depends heavily on geographic location, meaning drivers in cloudy or northern regions will still need to plug in regularly. But in many parts of the world, the Aptera could run effectively indefinitely without refueling or recharging, an automotive perpetual motion machine powered not by fantasy but by sunlight. As of 2025, Aptera Motors continues to refine the production model, with pre-orders placed worldwide. This approach aligns with a broader industry trend toward integrating solar tech into vehicles. Hyundai, Toyota, and Lightyear have experimented with solar roofs, but Aptera remains the most extreme example of full solar integration.